Hello, everybody. Welcome back. And last time we were talking about this idea of momentum, and we were talking about how momentum is a description of an object's motion, much like kinetic energy is, except for momentum has this vector property that it depends on the direction it's traveling. So, momentum is an incredibly useful quantity to understand, but so far we've only really talked about an object having some value of momentum that you find by multiplying the mass and the velocity together. But obviously, objects change their velocity all the time. And since they change all of their velocity, we might want a way to describe an object's changing momentum, how an object changes motional quantity. And the way we do that is with this new quantity called impulse. We say that an impulse changes an object's momentum. Now, what does that mean physically? What that means physically relies on sort of our already built understanding of how motion changes, right? We go back to this idea of Newton's second law, which tells us about how motion changes, and specifically that the force acting on an object, a force changes an object's motion, and that object's change in motion is described by an acceleration. So we have this F equals ma formula that we started with, and that was a really good first place to begin. But obviously this doesn't relate to momentum, right? This is just force and acceleration. Although we can do something here. We can take F equals ma, right? And instead of writing acceleration, what we're going to do is replace that with the definition of acceleration, which is the first derivative of velocity with respect to time. And now we start to panic a little bit. It's a derivative, oh no. But don't worry, because things become a lot more simple when we rearrange this a little bit. Because what I'm going to do next is put that mass into, put that mass into the derivative. So now it's mass times velocity dt. And we start to recognize that relationship mv, that's exactly how we defined the momentum of an object. So we can replace that mv with momentum, p. And we say that the force acting on an object is the derivative of momentum. And what's interesting is this is actually how Isaac Newton first defined this law. The second law is that the force is related to the derivative of momentum. And that's because in the time of Newton, we really understood motion as being related to this momentum quantity. So we have forces dp dt, right? And I said it gets simpler, and here's where it gets a little more easy to see. When we take this and we multiply dt by both sides, we get f dt is equal to dp. And we can integrate both sides. We integrate the left side, we integrate the right side. And what we're left with is f dt, the integral force with respect to time, is equal to the change in momentum. And that's ultimately what we were talking about earlier. We were talking about this idea of change of momentum. I said impulse causes a change in momentum. Well, here is your change in momentum. And that means this part, it must be that impulse that causes it. So we define the impulse of an object to be exactly this quantity, the integral of the force dt. And where things get a little more simplified is when we take this force to be a constant. So if the force is a constant, if and only if the force is a constant, what this does is it defines your impulse to be force times delta t. force times the change in time, or the amount of time that you apply to the object. So your impulse is the product of force and how long that force has been acting on an object for. So you take an example of, last time we used the soccer ball as part of an example. Why not continue with that? So we have this soccer ball here, my rough sketch of a soccer ball. And if we apply a force for some amount of time delta t, we would say that the impulse, and we actually use the letter J here to represent impulse, the impulse is given by F delta t. So we can map out the impulse as F delta t. And this tells us our change in momentum. We'll get more to that in a second. But if we had a second soccer ball, same mass for this soccer ball, we apply the same force on this soccer ball, but this time we apply it for an amount of time, not delta t, but 2 times delta t, twice as long. We apply the force for twice as long. That means the impulse is going to be force times 2 delta t. Or in other words, it's going to be twice as large as the original one. And the fact that this force acts on it for twice as long, well, that's going to tell us it's going to have a larger momentum. And in fact, we would say that this second soccer ball achieves twice the change in momentum as your first. And that's just to say it's moving faster. And this maybe makes sense to us if we apply a force for a longer period of time, then of course the object is going to move faster. So our impulse tells us about this change in momentum. And for a constant force, we can always define that impulse to be force times change in time. If instead our force changed over time, though, what happens if our force changes over time? Well, if our force changes over time, we have to use the idea that our impulse J is equal to the integral F dt. We must use that. But here's the good news. The integral, well, in this class, that has just been a fancy representation for if we take a graph and we graph out the force, and we'll say force in newtons over some time t, the impulse being the integral of it, this is just to say that the impulse is the area under the curve. So this area I'm marking out in orange is the area under the curve, and that is our impulse. So we graph it out. We graph it out and we find that the impulse is the area under the curve of a force versus time graph, and I should probably say seconds, why not? And we then ask the question, well, how does this help us with our problem that I initially said about defining our impulse? And what's interesting is we can say that given some average force, if we have some average force, if we could represent this force as just being some averaged value over time, the area under the curve of this average force, given by this lighter green area, well, it ends up mathematically being identical to the orange area, meaning that that average force gives you the same impulse, as your original force. So what we can say is that our impulse here is given by F average, the average force, multiplied by delta t. So even if we have a non-constant force, such as this red line right here, even if we have this non-constant force, we can always represent it with some average force, and that average force is a constant force. And it gives us this simplification. So where does that leave us? That leaves us with this idea that your impulse can be represented in a number of different ways, right? If it is a constant force, we can say it is equal to that constant force value, and again, only constant force, multiplied by delta t. Or if we are given a force that is changing, we can say it's the integral of the force dt. Sometimes that's useful. Or if we have some average force, we can represent it as the average force, not dt, rather delta t. The average force multiplied by delta t. And in each of these cases, what we know, and this is what we defined in the beginning, is that that impulse J is exactly equal to our change in momentum. So our impulse can tell us our change in momentum. And we take this and we say, okay, well, how does this apply to anything? And we can start to analyze questions of how much force is being applied to an object to get it to change its momentum. And then we can start to find other relationships, other important relationships that can help us do things in our physical world, such as make safety devices for our car and determine how the motion of certain animals and even rockets work. So this becomes a very powerful tool, a tool we'll use over and over again in our discussions. Before we end this, let's talk about a brief example, though. Let's use the example of a tennis player serving a ball. And if we ask the question of a tennis player serving a ball, we might be concerned with the question of how much force is that tennis racket actually impacting the ball with. So here's a tennis racket. And the tennis racket is going to impact a tennis ball, sending it moving with some velocity. Now, a couple of useful pieces of information for this problem. The mass of a tennis ball is typically about 0.057 kilograms, about 57 grams. If we're talking about a professional tennis player such as Venus Williams can hit a ball with a velocity that's after the serve of about 58 meters per second. And for any serve, the initial velocity is going to be 0. It starts from rest. The time of impact for the tennis ball, well, in a typical serve, the time of impact is going to be about 5 milliseconds, or 5 times 10 to the minus 3 seconds. And when we ask the question of how much force is the tennis racket impacting the ball with, well, how we're going to solve this is first determining the change in momentum. And once we have that change in momentum, we can then determine the force from the impulse, right? The change in momentum, the impulse, and that would be over time if we're talking about an average force. So let's go ahead and put this into practice. Change in momentum, delta P. Your change in momentum is going to be Your change in momentum is going to be the mass multiplied by your change in velocity, v final minus v initial. When you calculate this out, you'll end up with a change in momentum of 3.3 kilogram meter per second. This is exactly what we were doing last time. And we know that our change in momentum is equal to our impulse, so our impulse is also 3.3 kilogram meter per second. With that in hand, we can then take this and say that our force on average, as the tennis racket hits the tennis ball, is going to be the impulse divided by the time that it's been traveling, and that's going to give you about 660 newtons of force. So quite a bit of force here, and a tennis player does hit a tennis ball with a lot of force. All right, so I'm going to stop this video here. Hopefully at this point, you can do a couple of things. You can explain what impulse is. That is to say, impulse is the quantity that causes a change in momentum That's what it does. And it is calculated by taking the force and multiplying it by the distance. And in the case of a non-constant force, meaning we have to take the integral of it. All right, next time we're going to talk about an idea called conservation of momentum, and that is a useful tool in solving more and more complex problems and making more and more complex predictions. If you have any questions, feel free to reach out. Otherwise, I'll see you in the next video.